So welcome everybody to this week's Green Bank Observatory Community Zoom. I'd like to give a little update on where we are with the telescope, just to let the community know what to expect in the next few weeks. So first of all, I want to advertise our 13th Single Day Summer School, which is going to take place in August. It is a hybrid meeting. We will have slots available here for live participation at Green Bank. We can also do remote participation. So if you're a graduate student or a professional looking into move into radio astronomy, this would be an excellent opportunity for you. And the applications are on our website. I wanted to give you a quick update on where we are with our infrastructure and the damaged wheel and the foundation. So in early January, a piece of metal broke off one of the wheels and prevented our movement of the telescope on this damaged wheel. You can see this is a pretty hefty chunk of metal about the size of a fist that came off. We've since have replaced that wheel. So we replaced it a few weeks ago. Here's the team heroically working on it. The new wheel is there. This is the old wheel, actually. That's the old wheel coming off. We had to lift it gently with a very large crane. We had to tip it over with a forklift and a crane. I'll just run a little bit of this just to see that it's kind of an industrial operation there. So the forklift held it on one end and the crane lifted on the other end. We had to tip that whole assembly over to disassemble the housing and remove the wheel. After all that, the new wheel has been replaced with our spare. There's the spare, and the telescope now moves. So yay. Good work by our mechanical engineers and our telescope mechanics team to get that up and running. So we have found a bit of damage on other wheels. This is minor damage. So there's a spall on one wheel about the size of a quarter. There's a crack a few inches long, a little pinhole in the middle of it. Luckily, this crack is a little bit more concerning because that's some of the material around that crack. It looks like it's about to come loose. Now, of course, we have been running these wheels for 23 years. We don't know when this crack formed. So fortunately, this crack is longitudinal rather than radial. So even if some spalling does occur, the wheel should hold. So that's where we are. We've inspected about 75% of the wheel surfaces now. We have another quarter to go. We may find another crack or two, but luckily we have not found anything significant in our inspections. So moving forward, I want to stress there is no danger of structural failure possible due to these damaged wheels. The areas affected are quite small. There are 16 wheels that support the structure, and the failure mode of the wheel is a small spall, a small divot in the wheel, and not the complete disintegration of a wheel. We're working with vendors to acquire new wheels, pending the results of inspection. If we find no major damage, we will resume operations when the foundation work is complete. More about that in a minute. We will, of course, keep a close eye on the slightly damaged wheels to ensure that the damage doesn't get worse. And we will replace the damaged wheels during normal summer shutdown. So that's where we are on the wheel situation. The other thing that's happening is we're working on the foundation. There's an area of the foundation that shows some undermining or damage to the concrete, and you can kind of see it here. This area had kind of loose concrete. It was at one time concrete, but has since degraded into what looks like sand and gravel. So that is obviously not desirable to support the weight of the telescope as it rolls over. So we need to remove this damaged concrete. We need to replace it with new concrete. And the extent of this area was a bit larger than we had originally anticipated. It'll take about 3 more weeks before operations resume. So I apologize for the downtime. I know people are eager to get back on the air, but we want to do this right and want to make sure that the telescope is structurally sound and will live to support operations for decades to come. We all have our bad hair days. but we will clean up very nicely and the telescope will be beautiful once again. So with that, I will pass it off to Dave Freyer, who will introduce today's speaker.
Thanks, Jim, and thanks for sharing some of your bird pictures. We're happy to have with us today Ingrid Stairs. She's joining us from the University of British Columbia, and she'll be talking to us today about test of strong field gravity with the double pulsar. I'd like to remind our participants, if you have questions, put them in the Q&A box down at the bottom of the Zoom window, and I'll just go ahead and hand it off to Ingrid. It is all yours, Ingrid.
Yeah, thanks, David. So hopefully my sound is I'm glad to hear the GBT is going to be back in action soon. And I'll also say I was a Jansky Fellow in Green Bank way back at the time of the first single dish summer school. And I got to talk about how to do calorimetry. Carl Hylas and I tag teamed on that. So that was an interesting experience for the students, I'm sure. So it's a great thing to go to if you're thinking of switching into. So yeah, today I'm going to talk about a result that was published a bit more than a year ago, but I want to make sure everybody who loves Green Bank is aware of the result, because this is the timing tests of gravity with the double pulsar. So, you know, there's a cartoon of the double pulsar. This is the only known system where you have two neutron stars orbiting, both of which have been visible as a radio pulsar at some point. We have been stuck only seeing the A pulsar for the last 15 years or so. It disappeared sort of late 2008 because the spin axis of the B pulsar was processing out of our line of sight, or taking the emission zone out of our line of sight. We think it might come back one of these years. We have the historical record that it was visible as a radio pulsar, and some models of the geometry that, you know, as I said, suggest it might come back soon. So we sort of hope that will be able to time both again. But we can learn a lot just from timing A, and that's you know, because this system is really one of the most relativistic double neutron star systems known. So it completes a full in just 2 hours. The eccentricity is not huge, but it's still big enough that all of the effects predicted by general relativity are quite large and quickly measurable. You know, the sort of standard ones, and we're now into the era of need to measure further effects than have ever been seen in double neutron star systems before. So the typical orbital velocities for these things is 300 kilometers a second, right? So, you know, the well, 0.1% of the speed of light, very, very fast. And, you know, the orbital separation is also very, very small. So, as I said, keep focusing on that because that's the one that's visible now. And I just want to give you a little bit of context for why we want to do this. And that is because using these double neutron star systems to probe the effect gives us access to a regime that you can't get to with the solar system, for example, where we're very much in the weak field approximation. So here's a plot of the gravitational potential axis versus space-time curvature on the y-axis. So you can see in the solar system, you know, even the Cassini experiment, we're still very much in the low curvature regime, these logarithmicals here. Even though, you know, the gravitational potential is in how close you get to the equivalent of a point mass, it can be pretty large for the Cassini experiment. And, you know, these experiments, Star and M87 with the EHT, you know, yes, you get up to a very large gravitational potential, but still fairly small curvature because, you know, supermassive black holes event horizon is pretty large. And so the curvature isn't. To get to the high curvature regime, you really do want to go to, you know, double neutron star systems or, you know, black hole mergers of the type that LIGO can also see. So, you know, clearly not at the point where things are coalescing within, you know, 30 seconds or so as LIGO sees, but even with the, you know, 3 hour, 2.5 our orbit we have lower regime of space-time curvature than the solar system and so on. So the reason this is interesting is that in some theories of gravity, alternative theories, which people keep and which we keep trying to squish down, it may be that the coupling to the extra fields, the extra parameters that show up in these theories of gravity might depend on the neutron star structure. Getting into this regime where we're really passing close to very compact objects like this is telling us something different from what we can access in any other part of the space for testing. So a quick reminder of how pulsar timing works. If you build up a signal over many hours, you get a standard profile, and this is the one for the double pulsar at 820 megahertz using GBT data. It's looking a little pixelated, sorry. And any one observation that you do is basically a reproduction of that stable standard profile with some added noise. Now, if you have geodetic precession happening, then the profile can change over the long term, and you have to account for that. Interestingly, we don't have to do that for A, and talk a bit more about that in a second. So the name of the game for pulsar timing is measuring the phase shift between the standard profile and the observed. We do by cross-correlating within the Fourier domain and choosing a fairly large number of harmonics to accomplish the measurement. And that gives us a very precise phase offset. During the period of the pulsar, from previous observations and bootstrapping forward, we can convert that to a time offset and get a time of arrival by using the observatory maser to create that. Of course, the time of arrival is in the telescope reference frame, so we have to convert everything to the solar system barycenter, and that's how well we know that finds its ephemerides, but we have a pretty good estimate of that. And at that point, we enumerate all the pulses that ever came from that pulsar over decades and start to fit the parameters, like the spin down rate, position, the binary parameters. And so then we look at our best fit model and get the predicted times of arrival from that, subtract from the actual arrival. So I'm going to show you, a few residual plots over the course of the next 10 minutes or so. This is the kind of thing we're aiming for, where the residuals are nicely centered at zero, more or less Gaussianly distributed, no systematics. This is, showing that we have a good understanding of, this pulsar, 1713, but, we'll see we have that now for the double pulsar as well. So here is a display of all the data that went into this recent paper. So we did use data from many different telescopes, including Parkes, which has the longest timing baseline, but really the GBT was for all of the observations because it has the most sensitivity of any of these things here. Sorry, just waving to someone. And we got on to the GBT with the double pulsar early on with the Green Bank astronomical signal processor that I helped to develop along with Don Backer's group and David Nice. And so, we have observations at L going back along, and we used Guppy then as soon as that became available. And of course, we recently switched over to Vegas. We have very good frequency coverage. We subband the data so that we can look for changes in the dispersion, the DM as we call it, which is basically the electron column density between us and the pulsar, and that changes over time. So we need to look at different frequencies to correctly model the changes in DM. That got multiple points at each epoch. But you can see we've had good success with the TAC and very regular observations, with of course a few shutdowns here and there. But really, the DBT has been absolutely essential. So it took us a long time between timing papers. I will admit that, but that's because there was a lot to figure out. So we had this Kramer et al. Paper in 2006, and so we did have to persuade the TAC over and over again that really this was worthwhile and we were going to get there, and we did. But those dispersion measure variations about those can delay or depending on which direction the DM is changing. And if you don't correct for those properly, you can skew your measurements of other parameters in the system, right? So the parallax from timing is a big one that depends on the DM, but really, if you get the DM wrong, you can also end up affecting the binary parameters, getting the wrong mass and so on. So you really have to first carefully do measurements and account for those, subtract those from the timing. So we mostly use the Parkes data for that, actually. And though we did also bin down some of the GBT algorithms. We use these 4-minute integrations, fitting out the DM variations and sort of a constant offset also between the bands at over 100. So we did a couple of things. We did fixed DM bins over the 100 days. We tried different intervals, not just 100 days. We did some smooth fitting. Yeah, but the most reliable thing was to fit these bins of dispersion measure and common mode offsets over roughly 100-day intervals. With that in place, like this, and we used a Gaussian learning process then to sample that and make a smooth function out of it. So that's what the gray zone is here. It's the line is the gray region gives you sort of the uncertainty at all times. So this dispersion measure variation, so this is in DM units of parsec per cubic centimeter. It's definitely significant, and it matters to get that out properly. So what we did then with this Gaussian learning process output was do a Monte Carlo of all the timing. So sampling from this gray region, like sigma, or use the full distribution really, but using this process as what the DM had to follow, sampled from that, and then sampling it differently in order to get the best possible timing results. So this did allow us to get a timing parallax, which is not enormously significant here, as you can see here. So we also relied on the VLBI parallax, which was Adam Deller's major contribution to this paper. We'd been taking data, well, earlier on with the compact array, but also with the VLA, or VLBA rather. And you can see there's a definite signal here for the parallax. The result is not incompatible with the timing fit, but it's a lot more significant. We ended up taking the weighted average in blue here and using that as our parallax value. So again, we were sampling from that parallax when doing timing on the blue distribution here. So here's what it all looks like. Okay, and it's split up between the GBT 820 and 1500 megahertz. We did at 820 to look for profile variations. Parkes data, and I'll say we didn't put in Jodrell and Westerbork in here. But you can see everything looks pretty Gaussian. There are histograms, and here's the overall picture. There's this gray line here shows where the pulsar passes behind its companion. So you expect the Shapiro delay to be important, and you want to make sure you've modeled all that correctly. So you've got to sort of pay special attention to that point in orbital phase. These here are just versus days. So we're confident with timing solution. All that Monte Carloing really led us to a good value. So what we're most interested in for the purposes of testing GR are all of these so-called parameters. Right? So you can describe the binary orbit by 5 basic parameters: orbital period, the projected semi-major axis, the eccentricity, the longitude of periastron, and the periastron. And then you can start to fit relativistic corrections to these things. So we have the advance of periastron, analogous to the advance of periastron of perihelion of Mercury, but we measure it now not just to post-Newtonian, second post-Newtonian order, and it actually depends on the moment of inertia of pulsar A. So we're starting to get a constraint on A's moment of inertia. Not a measurement yet, but it can compatible with other one, laser. We measure the time dilation and gravitational redshift, this, from the signal having to emerge from the potential well of the orbit. And the orbital period, this is the loss of energy due to gravitational radiation. So, that's what Hulse and Taylor got the Nobel Prize for 30 years ago. Measure the range and shape of Shapiro delay. These are things that have been measured in several pulsar. Delta theta is something that has recently been measured in the Hulse-Taylor pulsar about 5 years ago, and we've got it now too. And it's basically a relativistic deformation. So instead of a perfectly elliptical orbit, even accounting for the fact it doesn't close due to GR, it's actually sort of a little more egg-shaped. It's a little pointier than elliptical. And then we have this new term here, which has never been measured before, which we're calling rho NLO, next to leading order terms in Shapiro delay and aberration. And I'll wave my hands and explain that stuff in a couple of slides. So here's a cartoon, which many of you have probably seen before. I think we can skip right here, because this is where we're finding this new thing. That's where the rho NLO comes in. So this is the orbit here now with the position of superior conjunction centered, right? So this is the true anomaly plus the longitude of periastron. So it's making sure everything's lined up, but with the 90 degrees being where the pulsar is behind the companion. So this is the full signal of the Shapiro delay here, right? It's really a nice peak. Now, the reality is that we absorb some of that signal into a redefinition of the projected semi-major axis of the orbit. And so when you do that, you're left with this signal here, which is still plenty strong. We see that it goes from microseconds peak to peak down to, well, about 100 if you're generous and include this dip below zero here. So it brings the signal down a bit. This is what makes it hard to measure Shapiro delay in very circular orbit systems, for example. So our red line is the best fit here. And then if we subtract that from our TOAs, these are bin average TOAs, we see there's still a little something left over. A couple of microseconds, data that doesn't line up perfectly on those red lines. So this is where this next to leading order term comes in. So this is a combination of two different things. The Shapiro delay effect. So it accounts for the fact that the B pulsar is moving as the signal from A is coming toward you, right? So is that motion of B across the orbit is changing the potential a little bit as the other component is an aberration term. So it's accounting for the fact that A is spinning, and this is hard to do, but A is spinning signal from its surface. So the signal gets, slowed down a little bit when the pulsar is on this side, assuming that it's spinning this way. It will get slowed down a little bit on this side of the orbit and a little bit as it whips around once it's gone past the B pulsar. If it's spinning the other way, you'd expect it to slow down or to speed up over here and slow down over here. So the sign of this signal round, if you had the A pulsar spinning, opposite to the orbital angular momentum. But the fact that we've got this sign here with the delay speeding up afterwards means that we know now that the A pulsar's spin axis is very well aligned with the angular momentum. We actually had some idea of that before because A doesn't change over time. So we knew it had to be either aligned or anti-aligned, and this breaks that degeneracy perfectly. Just for evolutionary reasons, you'd expect alignment more than anti-alignment, but it's really nice to have another avenue at this. There was also a way of looking at the timing of the B pulses that led us to that conclusion too. Oh, here's the term. Yeah. So here's the what I was just waving my hands about, and here's the law changes in A. Right? And like I said, we can also get at the same conclusion for modeling the B pulses. So now we have three avenues of observations of which all basically tell us that the A spin axis is perfectly or nearly perfectly aligned with the orbital angular momentum. Here is the famous Halson-Taylor equivalent plot of the cumulative shift of periastron over time. So, 15 years or so of data. And, there are error bars in all these points. They're just really small. And this is if you take an orbit, at each of these little time intervals and measure exactly when the periastron time happens, right? You would expect it to go on a flat line here if there were no gravitational wave damping. But the gravitational wave damping prediction means that you would expect this parabolic decrease in the T naught basically over time. And so we see that quite beautifully. We do have to make a correction to the observed PB dot, as we call it, the orbital period decay. And that is because there's a small relative acceleration of the solar system barycenter and the pulsar system center mass. So a lot of that is due to the galactic potential. Some of it is due to basically the Doppler effect of the pulsar having some transverse motion. So it's a bit like an ambulance. And the combination of those two things gives us the size of the correction. It's hard to do because we've got a v squared over r term there from the Doppler effect. And then of course, the gravitational potential of the galaxy, we also need to know how far away it is. So the fact that it was difficult to get a really good distance measurement until we had VLB, that this was also something we really had to struggle with. We've got a pretty good measurement now. This is our best estimate of the distance here, this turquoise line. This was an earlier estimate. But see that, you've got the v squared over r term here and the galactic potential here. When you sum them up, you actually get a curve that's pretty flat, which is really useful. It actually to make here does not depend very strongly on the distance. And so even, if future measurements shift the distance by a little bit, it's not going to cause an enormous problem for our understanding of where the PB dot curve should lie. So here's our mass diagram for, pulsar A mass on the x-axis, pulsar B mass on the y-axis. So back from when pulsar B was active, we were able to get the mass ratio of the two pulsars just from the seesaw effect of the two sizes of the semi-major axes. Everything else here comes from the timing. So with P dot, the error bars here are so small that everything looks like a line. The advance of periastron omega dot, the Shapiro delay here in blue and light purple, and the time dilation gravitational redshift here. We don't have the delta theta on there, but it's in there as well. The light blue here is a measurement of A's geodetic spin precession rate based on the eclipses of B, which is a whole other talk. And that's from René Breton's measurement back in 2008. So we can't glean too much from this plot. Everything looks like it lines up nicely, which is what you want, right? Because we may have 7 things that each depend on the two masses. So we have a very over-constrained system. And if GR is correct or some other theory of gravity is correct, you want everything to, have one consistent region on this plot where things work. We have that for GR, right? That's what's shown here in the blow up. So not everything is featured on here because some of the error bars like R get to be bigger. But we've got time dilation, gravitational redshift here, gamma, Shapiro delay. The PB dot is in purple, and then we've got a few different lines here for omega dot, right? So this goes back to what I said about constraint on the moment of inertia of A. Our raw measurement is here, this line, but we're at the point now where the moment of inertia of A will spin orbit coupling and cause the orbit to shift a little bit also over time. So we need to know what the moment of inertia of A is. That's going to depend on the neutron star equation of state. So we've got range here, soft equations of state here and very hard equations of state over on this side. And so we've sort of gone middle of the road here with our best estimate of what a equation of state would give us. So, what we do get from this is that everything lines up. We don't yet have a narrow enough PB dot region to, tell us exactly which equation of state is right. But getting to have a bit of a constraint, an upper limit at least, on the moment of inertia. And yeah, here was that the orbit into a sort of a pointy egg shape. We can go past that and let's look at the moment of inertia a little bit more here. So, LIGO has also come up with a equation of states from the 1708-17 event, and NICER has as well, right? So we've got the LIGO constraints down here, I think it is, and the two nice constraints. These are their measurements, and the blue stuff here with our 90% contour there, those are our constraints based on keeping our omega dot value compatible with PB dot. So, we're sort of right in the ballpark where you might expect the moment of inertia to be. It's a sensible upper limit, and if we keep observing over the next 5 to 10 years, CAD and SKA is necessary, but hopefully still continuing with the GBT a while longer. We should be able to actually make a measurement of this. So right now we have a rather boring upper limit on the radius, 22 kilometers at 90% confidence, but that should tighten up quite a lot as time goes on. Why is this not advancing? Okay. Finish up showing you what can happen for a theory of gravity that doesn't work. So this is, we can sort of skip this one a little bit, but talk about the right-hand side here. So this is a mass-mass diagram. Same thing, taking those multiple curves that all depend on the two masses in different ways and working out what their curves should be in the case of, in this case, a version of Tevez with one parameter set to 0.04, which gives you sort of a smooth transition from the Newtonian to the Mondian type regime. And you can see there is no really great intersection here, right? There's a few points that kind of arguably intersect there, but gamma's way off, right? So this can be ruled out. This is an example, right? There's a sort of, you can put a constraint on the level of the parameter here for Tevez, but Tevez is also in trouble because of LIGO, right? But this is an example of what we're able to do, like to actually rule out particular classes of theories. Over here, we're looking at the parameter space for the De Morgan-Esposito-Farez gravity, which has a linear and a nonlinear coupling. So linear is the A, and nonlinear part of the coupling is beta naught, alpha naught, beta naught. 737, the double pulsar cuts out part of the parameter space there. So again, it's dependent on the equation of state of the neutron star, because this is a particular case where the composition of the neutron star matters for the coupling to the field. But there's a little chunk of the parameter space here where it does better than Cassini or any of the neutron star white dwarf situations. I'll just give you a little view. This was published a year ago, so also of Meerkat data on this thing, where the eclipses of A show up just beautifully, and we're working on modeling those. Michael Kramer is a student focused on modeling that. So we're going to end up combining, the eclipse observations for the GBT over 15 years with the Meerkat data and producing a good result sometime in the next year or so, we hope. And I think I'll leave it at that. We have, as I said, a whole bunch of avenues pointing to pulsar A being prograde, lined up with the moment, with the orbital angular momentum. We have a constraint on the moment of inertia. And then, of course, down the road, Canada is getting into the SKA. I hope you will too at some level. And, there's hope for finding even more exciting and more relativistic systems. So I'll end my talk there and take some questions.
Thank you, Ingrid. So the Q&A is open, so feel free to type in your question.
Okay, I'll just, I can see a couple of these questions here.
Yeah,
so
you want to take them? Okay, if you can see them, you can just
I can see them. So if people type them in, yes. Otherwise, I guess people can't raise hands, I guess. So AC asks, before its signal disappearance of B, was the precession rate of the pulsar be modeled or determined? So there is a very nice formula derived by Barker and O'Connell and DeMoor and Ruffini back in 1974, around the time the Hall's-Taylor pulse discovered, which tells you what the precession rate should be. So the time for the spin axis of B to go all the way around is 70 years, I think, and for A it's 75. I think it's that way around. So the we knew what the precession rate should be, and we took that into account in making the predictions for when the beam ought to become visible again. We also had to go by for the beam that we saw over the years and try to come up with a coherent model of what the emission patch on the pulsar surface should look like, right? So there are a couple of different possibilities there. And it could be even more complex than we had modeled. So, there's some work to be done there. Okay, Dan, the EOS constraints are impressive. Thank you. What are the prospects of improving those over the next 10 years? Well, I was trying to get to bringing in longer term data, Meerkat and SK and so on. We do think with a few years of SKA data, we will have it nailed. The IS propagation delays contribute to that. No, not so much. The time variable scattering delays. So what we need to make it an EOS measurement is, if I go back in my, go back to play. If I go back here to the mass diagram, what we need is to shrink the error bar PB dot so that it points to a particular region of this gray smudge here that we would consider acceptable. That's going to give us a good measurement of the moment of inertia that way, and obviously therefore the equation of state. So to do this, it basically just takes time. The uncertainty PB dot improves, just the experimental uncertainty improves as time to the -5/2, or t to the 5/2 if you're talking about how the uncertainty improves. But anyway, it gets better very fast. At some point, the uncertain distance will become a limiting factor. However, if we have the SKA involved in this, it's also going to give us an even better VLBI distance than we have now. And so that should take care of that problem. So that, it might be the galactic potential that is the limiting factor then. But we really ought to get there. I think that's the major systematic, and not the DM modeling so much, or scattering delay. All right, Alex Stafford, since you have a bound in the moment of inertia, have we looked into any I love Q relations to try and get a better understanding of the system without a specific EOS? I don't think we have really done that yet. Norbert Vex was the person really taking care of the EOS calculations, and it came up in our discussions, but I don't think we've gone beyond that. I mean, it's really just a greatest constraint at this point. Stacy, it'd be great to apply this test to theories like AEST, and Bimond, sure. I mean, all we do is work out how the parameters there would relate to the equation of state of the neutron star, if at all. Maybe they don't really, but we could pick any of these theories, choose a couple of parameters, and make the same kind of mass diagram. I mean, ultimately, we could derive constraints on the parameters for it, I suppose. Yeah, I mean, there would be great to apply them to other theories for sure. Paul Hemingway, do you have the value of the Lense-Thirring effect and how well it is separated from the other parameters? So, well, that's sort of what we're getting at with this moment of inertia thing here. This is basically due to the Lense-Thirring effect. It's spin orbit coupling. And so it's going to depend on the radius of the A pulsar. And, so using the plausible range of radii, we get this gray region here. I mean, it's not entirely separable from the other parameters as it is now, because it's effectively an extra contribution to the omega dot, right? So the advance of periastron. But we know what the GR prediction is there, right? So if we say we know what the plane GR prediction is, up to the 1.5, and then we bring in the moment of inertia, addition to that, right? We end up with something in this range here, as it then is to get the error bar on the PB dot to shrink way down so that we can actually isolate a region in this gray smudge that we think is really the best description of it. So, I mean, again, you can predict how big the Lense-Thirring effect should be, right? But it does depend on the moment of inertia of the A-pulsar. So we don't have one value, we have a range of values right now. No other
Yeah,
questions?
I'm not sure if there's any more questions. We'll wait here just for a little bit.
Sure.
As we're waiting, I'll thank Ingrid again for presenting today. And the next community Zoom will be March 15th. Gasper Gallez from Chile, the University of Chile, will be talking about the molecular gas content of the giant low surface brightness galaxy Malin 1 using the GBT and Argus. So I haven't seen another question come in, so we're going to call it a day. So thank you, everybody. And thank you, Ingrid, again, for giving the presentation.
Thank you very much.
Okay. Bye,
Thank you.
everybody.
Bye.